Meta-directing groups. When these groups are bonded to benzene ring, electron density at ortho and para position decreases through minus R effect, minus resonance effect or minus mesomeric effect. So groups or functional groups showing a minus R effect are meta-directing groups. Examples for meta-directing groups are all functional groups bonded to benzene ring using an atom involved in a double bond or a triple bond. As an example, COOH group. When COOH group is bonded to benzene ring, the direction of electron flow in resonance effect is away from the ring. Hence, ortho and para carbon atom becomes electron deficient. That is, ortho and para carbon atom get a unit positive charge. These are the resonating structures of benzoic acid. So here ortho and para carbon atom carries a positive charge. That is, ortho and para carbon atom are electron deficient. So when benzoic acid is subjected to electrophilic substitution reaction like nitration, nitronium ion will not approach ortho or para carbon atom, because ortho and para carbon atoms have electron density less due to minus R effect. So in benzoic acid, ortho and para carbon atoms are electron deficient, having a slight positive charge. So when it is subjected to nitration by heating with concentrated nitric acid and concentrated sulfuric acid, nitronium ion cannot approach ortho or para carbon. Hence, nitronium ion is forced to approach one of the meta carbon atom. Hence, substitution takes place at meta position. In other words, meta-nitrobenzoic acid is obtained. So COOH is a meta-directing group. Why COOH is a meta-directing group? COOH group decreases electron density at ortho and para carbon atom through minus R effect. In this resonance, functional group have a negative charge. Hence it is called a minus R effect or a minus mesomeric effect. Other examples for meta-directing groups. All functional groups bonded to benzene ring having using an atom involved in a double bond or a triple bond. One example is COOH, other example COOR, ester, COCl, acid chloride, CONH2, acid amide, CN, triple bond, cyanide, C double bond OH, aldehyde, C double bond OR, ketones, nitro group, N double bond O, coordinate bond O, sulfonic acid group, S double bond O OH. This type of functional groups are all examples for meta-directing groups. All of them, when attached to benzene ring, shows a minus R effect or a minus M effect. If it is COOR, this OH will be OR group. Rest of the resonating structures are exactly same. If it is COCl, this OH will be replaced by chlorine. If it is aldehyde, this OH will be replaced by H. So these functional groups, when bonded to benzene ring, electron density decreases at ortho and para carbon atom. Hence the electrophile is forced to approach one of the meta-carbon atom. Hence these groups are called meta-directing groups. As an example, when benzoic acid is subjected to an electrophilic substitution reaction like nitration, only meta-nitrobenzoic acid is obtained. That is, COOH is a meta-directing group. Similarly, when benzoic acid is subjected to bromination with bromine and ferric bromide under hot conditions, gives meta-bromobenzoic acid as the substitution product. When anisole is subjected to nitration, concentrated nitric acid, concentrated sulfuric acid, that is nitrate mixture, nitronium ion approaches ortho and para carbon atom because OCH3 group increases electron density at ortho and para position. So in this case, the product is a mixture of ortho-nitroanisole and para-nitroanisole. If benzoic acid is subjected to nitration, electron density at ortho and para position decreases. Hence, nitronium ion is forced to approach meta-carbon atom and the product is meta-nitrobenzoic acid. So, OCH3 group is a ortho-para directing group. COOH is a meta-directing group. This is the orientation effect of substituents in benzene. Consider one more example of orientation effect of substituent in benzene ring. The first compound is phenyl ester of acetic acid or ethanoic acid. Its IUPAC name is phenyl ethanoate. The second compound is an isomer of phenyl ethanoate. It is a methyl ester of benzoic acid. Hence, its a common name as well as IUPAC name is methyl benzoate. When these two compounds are subjected to electrophilic substitution reactions, nature of products obtained will be different. In the case of first compound, oxygen atom is directly bonded to benzene ring. Since oxygen have two lone pair electrons, this group can show plus R effect. Hence, substitution take place at ortho and para positions. When this compound, that is phenyl ethanoate, is treated with a solution of bromine in glacial acetic acid. Acetic acid is a solvent, glacial acetic acid. The major product obtained is para-bromophenyl ester, that is para-bromophenyl acetate or 4-bromophenyl ethanoate is a major product. Since both ester group and Br plus are large groups, there will be considerable steric repulsion and hence major product, around 95% of the product is para-bromophenyl acetate. A small amount of ortho-bromophenyl acetate or 2-bromophenyl ethanoate is also formed. In the second compound, C double bond group is directly bonded to benzene ring. Hence, there will be minus R effect. In other words, C double bond OCH3 group decreases electron density at ortho and para position through minus R effect. Hence, when this compound is subjected to electrophilic substitution reaction, only meta substitution product is obtained. In this case, the product is methyl 3-bromobenzoate or a methyl metabromobenzoate. Here the reagent is bromine in presence of ferric bromide. In both cases, electrophile is bromonium ion. So due to the difference in attachment, they behave differently in electrophilic substitution reactions.